screen. Okay, can you hear? Can you see it?
Yes, perfectly.
All right, very good. So, well, thanks to all for coming, and also thanks to the organizers and to Enrico, the previous speaker, for the nice talk. So I'm going to talk about work that I'm doing with Walter Tolan from York University, Toronto. And some of you may know already part of this work, which I presented a couple of months ago in a different seminar. So the idea is that we want to take colimits as if they were some operations of an algebraic nature. So let me maybe give an analogy. If you want to think about, say, commutative monoids, and colimits are like analogous constructions. So the idea is that, for example, if you have a set, then you can look at, for example, n-ary tuples, okay? Which, of course, in the category sets, you can also view this as map from n to x. And this gives you an element of x again, which can be seen as a product of these. And then there's a monad, which can be obtained by taking the colimits of all these. So the disjoint union, but we have to quotient under permutation. So it's more like the colimit in the permutation category, which is the category of finite sets and their permutation, so the core of finite sets, okay? Now with colimits, we have something analogous. So you have a category. I'm gonna make precise what I mean by category because there are some size issues, but bear with me for the moment. And we want to form colimits of a diagram. So instead of an n-ary operation, we have a diagram. So we have the indexing category, I and C. So you see that's similar to what's happening here. And given a diagram, we have to get, again, an object of our category, which is going to be its colimit. Now, keep in mind, a colimit is a bit more than this, because if we have a certain diagram, then its colimit is not just an object, but has an entire universal cone that satisfies a universal property, is defined up to isomorphism. So we may have other universal cones, and then the universal map is an isomorphism. But we can in particular forget about the universal cone for the moment and pick one of the objects in its equivalence class that is going to give us a map like this. And we get a sort of monad here too, but it's not just a colimit. So the monad that we get is more like, I would say, a colimit with arrows in the sense, well, a growth and deconstruction. So we have this contravariant functor, and then we get the growth and deconstruction, the contravariant growth and deconstruction of this, which is a bit like a colimit, except that some arrows are thrown in, which reflect the fact, just like here we want this colimit to be functorial in this variable, here we want to take into account functoriality in this variable. And this will be reflected by how we define the morphisms of diagrams.
It is a
So,
colimit, right? It's just a lax colimit. Am I right?
So the
The
covariant
the
one.
Grothe construction.
So the covariant one is the contravariant one too?
I guess it works the same way. I don't
Yeah,
know. I
just the variation.
might be. Yeah.
I don't know, but
Of course, lax colimits behave differently than pseudo or
yeah, no,
strict
yeah,
ones.
I agree. I'm not sure that this one can be expressed just as lexical limit. I'm not entirely sure.
Okay.
But so the important thing is that, let's say, in the spirit of lax colimits, at least, the stuff that on the left hand is identified, here instead we'll just have an arrow. Okay, so since we're talking about colimits and we want co-complete categories as algebras of our monads, we want to take care of some size issues. We don't just want posets like, as we saw in the previous talk, one has to be a bit careful with those issues. So let's say that cat is the category of small categories. And cat written all capitalized is the category of locally small, possibly large categories. Okay. So now, if C is a locally small categories, a diagram in C is a functor where I is small. Okay, so we just want small diagrams. The idea is that we want to take colimits of these guys. But most importantly, and here's where you actually see the growth in deconstruction, a morphism of diagrams is a lax triangle in this form. So we have D, we have another diagram from a different category, possibly J. Then a morphism of diagram consists of, first of all, a functor here, but also a natural transformation here. Okay? So keep in mind this is slightly different from the usual, because usually we want R to be the identity when we consider morphisms of diagrams as just natural transformations. So that would correspond up here in taking the disjoint union of these guys. Or like the coproduct. Instead, we are really using the arrows in this place, which gives us a fibration. So in particular, there's a forgetful functor from this category to just locally small category. So we call this category diag of C. Okay. So the forgetful functor to cat the maps this to just I is a fibration. It's a fibration with Cartesian morphisms given by those that in here have just the identity, so that just commute. Okay. So Are there questions until this point? Maybe before I go on? Seems not.
We have an observation from the chat where
Oh, yes.
Eduardo points out that the Grothendieck deconstruction is actually a colimit. It's just O-Plax. The covariant one is lax and the contravariant is O-Plax, or vice versa. It depends on your convention.
Oh, okay, perfect. All
right. I have one question. Can you
Yeah.
hear me? Okay. So I wanted to ask, is there a natural transformation or some kind of comparison between this construction of diagrams and the small per sheaf structure? There should be.
Yes, there is, and I'm going to talk about it hopefully very soon, actually.
Oh, thank you.
So yeah, let me just point out here that this construction of morphisms of diagrams is not so different from the usual one. Especially, it's kind of the same in the case that R is essentially surjective. So if there's a diagram here, this is D, and J may be a category that looks like this. I don't know. So we get a diagram with this shape. Then the natural transformation raw may be in this form. So instead of deforming a diagram into another diagram, it deforms the diagram into a sub-diagram of the new diagram, okay? So that's the only difference that you have if you use this notion of morphism of diagrams, okay? All right, so one thing that has to be said is that diag forms a monad. So, well, pseudo monad. I would say monads and algebras, but here we are in two category theory. So what these objects really are always pseudo monads, pseudo algebras, pseudomorphisms, and so on. Okay. On cat. Now, I suppose it's pretty clear what functoriality would do, and the unit 2. The non-obvious thing here is the multiplication. But if you want to know more about the monad structure, of course, feel free to ask. But the multiplication is interesting. So multiplication is given by the covariant growth and deconstruction. What's happening here? So the idea is that diagrams of C are pretty much the same as lax cocoons. How does that work? Well, suppose you have a small category and a diagram into diagrams of C. So what's happening here is that we have objects of I and now the first I is mapped to a diagram in C, which in cat looks like this. So di, let's say d0i. So d0 is the part of D that gives you the indexing category. D1 is the one that gives you the functor. The same happens for I prime. And small I gives us a morphism of diagram that we have seen as a functor and the natural transformation. So you see, this will happen for all the objects I of I, and so we will get a lax cocone with dip C, and so lexicon in cat with dip C under the D0. under the functor part. Well, actually, all these have to be small. Sorry. Okay. So now we use the fact that, as was mentioned before, and this time I'm sure it's true, that we have this lax colimit property. So again, lapse and uplax depending on the convention. So the idea is that, well, let me maybe rewrite it here in larger. If we have a lax cocone in this form, of course, imagine more objects than just two. Then the Grothendieck deconstruction, this time not up, will factor this natural transformation into this triangle where these diagrams commute. So it will contain all these as fibers. So you can consider these as like embedding in some way, but not. So there may be some additional arrows. And the important thing is that a diagram of diagram gets summarized into only one diagram, this one. And we call this diagram exactly mu of t. So mu goes from lax cocoons, so diag of C, to just diag of C. If you want, it packs all these diagrams together with and forms one diagram that kind of summarizes all of them. Okay. Let me also maybe give a reference. So I was not the first person to come up with this monad. It first appeared in this paper. So René Guittard, on the diagram functor, I guess that's the translation. That's in Kayers. So now I have to say it's claimed that this is a monad, but there is no proof. So it's pretty clear from the paper that the author knows what they're talking about, but it's not written. So it still took some work to figure this out, especially the coherences, which I would not go into unless you really want to see. Okay, so let's also say co-complete categories are algebras. So, of course, we have to make the terminology here a little bit precise. So we don't want to have size issues. So by co-complete categories, I mean locally small categories, possibly large, which is small co-complete. So colimits, the diagrams of which we're taking the colimit are smaller than the category, so to say. We don't get just opposite, okay? And by algebras, of course, I mean, again, pseudo. So the basic idea here being that, first of all, if you have a category C that's co-complete, then there is a map from diagram C to C. Let me just denote it by column. So what this is of course a choice of a colimit for each diagram. Okay, so we're using some kind of large choice here. It doesn't really depend which colimit we take in its equivalence class. Any choice of a map for each object, for each diagram, sorry, any choice of colimit would do, will make the thing automatically coherent because of the universal properties of colimits. So in particular, this diagram commutes. So what the unit here is taking is the one object diagram. And of course, its colimit is just isomorphic to just its diagram. And it's uniquely isomorphic. So that's why this isomorphism will be coherent. More interestingly, the multiplication some parentheses. Sorry, this is not type. This is just C. Also will commute up to isomorphism. And this is...
So is this monad lax idempotent?
I don't think so. I don't think so. So it's somehow more lax than that, I believe. And the reason is, again, I don't have a proof, but the suspicion I have is that, so it's because not all the algebras are in this form. So maybe one way to see this is that in particular, free algebras are not. No. So if you take a free algebra, the structure map is given by mu. So for pseudo algebra and pseudo monad, the same business of freeness is the same. So DIXA is going to be a pseudo algebra. The structure map is given by mu, exactly like for one monads. And the problem is that mu is not quite the colimit of this diagram of diagram, but it's lax colimit. So for example, if you take f from x to y in C with x different from y, even up to isomorphism, then you can form the following diagrams of diagrams. The first diagram is the one that picks out x. The second diagram picks out y. And there's a morphism of diagrams here.
Yes.
That gives f. Now you see that the growth in the construction will just give you this diagram where the image is again f from x to y.
Yes.
On the other hand, the colimit will just give you y. So in particular, the colimit of this will just have one object. So this is giving you the colimit of this diagram. Okay.
Okay.
If I may make a comment, this also shows that it is not lagdempotent, because there is a characterization of Marmolejo that proves that monad is idempotent even only if me is, I can't remember the left hand or the right adjoint to something, and in that case, clearly it's not. There is no universal property there.
Oh,
yeah,
nice.
That was,
Could you maybe give me a reference at the end of the talk? Because I've been wondering this for some time and really haven't.
It's not from Marmolejo, it's Anders Koch who introduced the notion of KZ monad, and there it's already proved that KZ means that multiplication is, I think left adjoint to the whiskered unit.
Yeah.
There's also a condition, algebras are
Yeah,
exactly the adjoints.
I'm
But
aware of that
with
characterization,
the
but
multiplication comes out more neatly because you just have to work with the monad structure.
I see.
Yeah, it's in the original paper by Koch on structure is adjoined to unit, something like that. Anyway,
I see.
sorry for the
Cool.
for
So
the
thanks a lot, actually, because this is solving something that I've been wondering for some time. So if I can ask you a reference at the end,
Of course, yeah.
I'll be
I
very
can.
happy to finally settle this. Cool. So this is not KZ then. And again, I don't have a complete characterization of all these algebras or pseudo algebras, but you see, I suggest maybe there's an analogous monad on the category of two categories, and this is taking again co-complete categories, but with structure map given by lax colimits. That is a conjecture. I don't know, but so at the very least, like lax colimits should be again algebra structure maps of this monads, in particular, not just the ones I've written down, but the one that I've written down are the ones that I'm interested in for the purpose of this talk. Okay. Okay. So, are there more questions about this? Okay, let's go on then. I want to talk about image presheaves. Now, I don't know if I've come up with this notion and this theory. I mean, some of the statements that I've proven are new as far as I know. I don't know if this concept has been given a different name though. If so, please let me know. So what I want to do is the following. I take a diagram. And I want to take its free colimit, which, as you know, is a presheaf. So the idea is that we take D to C. We have the unit embedding. And we want to take the colimit of this. All right. So we call this the image of D. Okay. And also, we call a presheaf. Sorry. Small if it arises in this form. Which equivalently, if it is a small colimit of representable. Okay, so you probably know every presheaf is a colimit of representables, but usually a large one. So we just want to consider the small ones. Okay, so small presheafs have been studied by, let me give a reference, Steve Lack and Ryan Day. So the reference should be limits of small functors. So that's in the Journal of Pure and Applied Algebras, 2007. Okay, so in particular, if you denote P, the small subcategory the full subcategory, sorry, not small, of small presheaves, then P actually is again a monad, I mean, is a pseudomonad. Which one can view as the small free co-completion, like free small co-completion. So you probably know that you can't really talk about a free co-completion monad if you take generic presheaves because of size issues. But if you take small presheaves, then it's all very good. And that's somehow the actual monad that you need here. Because usually when you want to talk about colimits, you don't want large colimits, you want small colimits. Otherwise, as said before, you just get rosets. Okay? And it turns out that, maybe let's write it here. M is a morphism of monads. I mean, as a pseudo morphism of pseudomonads. You may have suspected this already by the way we have constructed M, because, I mean, of course, this lands in P of C, really. I mean, obviously, one object diagrams are in particular small diagrams. And this is actually the unit of P. So you can imagine that the unit of this monad is given by the unit embedded, okay? And so we're taking the colimit already in the algebra, so that should give you an idea of why this is a morphism of monad. That the operation we're taking is actually already in PC. But in particular, you know that if you have a morphism of monads, then you get a pullback morphism between the algebras, sometimes called the restriction of scalars. So what I mean here is that, so first of all, what are the algebras of Phi? They are co-complete categories. Now all of them, like that's the monad of co-complete categories, again with a choice. How is the structure map working? Well, it's a weighted colimit, or like coend. I usually denote it by coend. So what I mean is that if we have P, then you get the following coend.
That's very bold of you.
Hmm?
Nothing. I'm kidding.
Sorry, why?
No. I'm kidding. That's
So
yeah. Nothing. Go ahead.
I guess
I was kidding.
You're the expert on coends. So,
but I agree in the end, so no problem.
Yeah. So what's happening here? So every small presheaves is in the essential image of this map, okay? So what's actually happening here is that P itself is, up to isomorphism, the free colimit of some diagram. So it comes from some small diagram. So this is the colimit. So let me write it again as a coend of not quite D of I, but home in C of this, the free colimit of this. Okay? So this thing is then isomorphic to sorry, I forgot an integral. So now we apply the usual Fubini. All these isomorphisms mean if one of the limits exists, the other one exists, and they coincide up to isomorphism. Huh? So they're not just that's of course normalcy. And now we apply Koyoneda, which simplifies the C. Which is by definition. Okay. So in particular, you see that this colimit exists because C is co-complete and I is small. So all of those exist and they coincide. Okay. So this just gives you an idea of how this is a morphism of monad and why, in some sense, why co-complete categories are algebras of the diagram monad, because they are algebras of P and there's this morphism of monad. So via the pullback. So pretty much like compare R to S, a morphism of rings, then S modules are canonically R modules via F. Okay, pretty much the same idea, just a bit higher dimensional. Okay, so are there questions until here?
I have one question. You get,
Yes, please, go ahead.
so you get a comparison factor between the algebras, which I believe is at least continuous, but I mean, let's say it's continuous for a moment. Does it have a left or a right adjoint?
So you're thinking about these extensions and co-extensions of scalars.
Precisely.
Yeah, so honestly, I haven't worked out the case for two-dimensional monads, so I don't know. I suspect so because in the usual construction, you only need your category of algebras to have reflexive co-equalizers, and then the construction just follows through. I strongly suspect one can do the same here, but I haven't done it. And for sure, I have no intuition of what that would give us, so I don't know. But yeah, that's a very natural question to ask, actually. So maybe, let's say, good questions. Good question. Extension and co-extension.
Sorry, do you expect both of them or just one of the two?
I would expect. Oh my God, which one of the two now?
Maybe don't
one
commit.
that takes. Sorry.
Don't commit yourself to full statement.
Yeah, I don't know.
Remember.
So the category of diagrams has like one of the two. In the category of diagrams, I don't remember which ones are nicer. So limits or colimits, one of the two is nicer than the other one. So I expect the one that comes from that side. But honestly, now I don't remember which direction that was. But so limits in the category of diagrams are actually, so if you want to reference, is Paschke and again, Walter Tholen. So diagrams, fibrations, and decomposition of colimits. It's a preprint on the archive of this year. So in particular, they explain very well this diagram right here. But yeah, so they figure out a lot of properties of limits and colimits in the category of diagrams. So I suppose that's the way to construct extensions and coextensions. But yeah, I haven't done it. But yeah, that's a good question, actually. It's interesting. I don't know what that would give.
I have a simple question, if I can.
Yes?
I was trying to parse your definition for the integral, the co-end of C tensor PC. As a
Yeah, so
weighted colimit, you say.
that's the co-power.
Yeah, you're using P as a weight, and
yes.
probably up to size issues, you are taking the weighted colimit of the identity, right?
Yes, yes, precisely.
Okay,
It's a
yeah.
weighted colimit of the identity with
Using
weights given
P
by
as a
P.
weight. Okay.
Yeah, exactly. Yes.
Okay.
So maybe just to check things. So when you have these small preshifts, can you see them as diagrams too? I mean, it's just a matter of size. I just want to check that.
Sorry, what do you have in mind? I'm not sure I understand
I
what
have
you
in
mean.
mind that you, I mean, every preshift should define a discrete vibration above C.
Ah, yeah.
And so I was just wondering,
Good point.
Size would allow you
Yes.
to do that or not really? Yeah.
So again, up to size issue, you're absolutely right. So that's actually the thing I wanted to say now. So suppose you have a small presheaf, okay? Then there exists, by definition of small presheaf, there exists a diagram, small, with image of D given by P up to isomorphism, okay? So what does that mean? We have a diagram like this, but now we can always take, so there's a canonical choice of a diagram that has this as an image, namely the Grothendieck deconstruction, again, the up one, of P, okay? The only problem, of course, is that this thing is possibly large, okay? However, by a factorization that's sometimes called comprehension schema, there is here a functor that's final or cofinal, depending on the terminology, more on that in a moment, that makes this diagram commute, okay?
Sure. So, I mean, the point is that you cannot see the Grothendieck construction as a diagram, and so you cannot map back one monad in the other. I mean,
no. However, you can then always take, so this is small, and F is final or cofinal, in the sense like a preserved colimits in a very strong sense. So you can take its full image.
No, sure, I understand. So
and so you can always, okay, let's leave F. You can always take a new small category J, which is a small full subcategory of the Grothendieck deconstruction, and it's embedded cofinally. So it's true, you cannot view the Grothendieck deconstruction as a diagram, but you can always take a sub-diagram that's actually small and that still has that as the image.
Thank you.
I hope that answers the question. So the term final, cofinal, some people call these co-initial, can be very confusing, okay? So it comes from the idea of a cofinal net, in that sense that co here is the Latin cum, which means something like with or together, and has nothing to do with duals, okay? So cofinal doesn't mean initial in the sense of cofinal functor, and this can be a bit confusing. So we would like to say that they have the same ending, so to say, so same colimit. Walter has proposed to use the word confinal to settle the issue, so that it preserves the etymology, but it does not sound like a dual. And I think I would like to stick with this terminology here. Okay, so definition: a confinal functor. See, today is the same thing as saying, so slice categories are non-empty and connected. So in the sense that, or equivalently, for every G from D to E, the colim of G compose F is the same as the colim of just G. And of course, if one exists, the other one exists, and they are and they're isomorphic. Okay. All right. So I don't have much. Can I ask a couple more minutes since I started a little bit late?
Yes, of course.
Okay, thank you. So I'd like to say a couple more things. So first of all, that we have a kind of a generalization of the theory of confinal functors. So the following conditions are equivalent for two diagrams into the same localist mode categories. A is that the images are naturally isomorphic. Sorry, of D. B, they're for every G from C to D, colim of G compose D, if it exists, is isomorphic to colim of G compose E. Okay. Again, if one of the two exists, the other one does too, and then in that case they are isomorphic. And C, there exists a zigzag from I to J, where all these triangles commute, and all these functors in the zigzag are confinal. Okay, so you see, C to A is pretty straightforward. That's just the confinal, the usual theory of confinal functors. C to B, sorry, is pretty straightforward. But what I want to say is that the image really captures this behavior. Okay, so we say in this case that D and E are mutually confinal if this happens. So it's more than having the small colimits, than having the same colimit. It's like as having the same colimits under the image of any functor. Okay. So the image is somehow a blueprint of colimit, and if they have the same blueprint of this colimit, then whenever you take their actual colimit, even after applying a million functors, those two will coincide. And the last thing I want to say, for those of you that missed my previous talk on the topic, is that can extensions are partial colimits. This is actually the statement. So the proof of this statement is the one that motivated all this work. And the way I came up with this statement is because it's very similar to something in probability theory. If you're interested, we can look into that. But the statement is actually two statements, so to say. So A, it says that so let me first maybe say something. So there's a theory called partial valuations that tells you that if you take the first two levels of a bar construction, so 0 and 1 dimensional simplices, so there's two canonical maps from if you have an algebra of a monad, you have two canonical maps at this level, right? There's mu and there's TA. These are like somehow the source and target maps of one simplices in the bar construction. So these have the meaning of partial evaluations. The classical example is that 3 plus 2 plus 1, of course, is equal to 6, but is also equal to 5 plus 1, okay? And so these two formal expressions that would live in TA for the case of the, let's say, free commutative monad, these would be connected by a partial evaluation of this form, okay? So that's the way to encode category theoretically, partially evaluating that formal expression. So if you do this for colimits, you get exactly can extensions. So if you do it for diag, turns out that D and E and DXC are connected by a partial evaluation if and only if, so if and only if there exists a functor here and a natural transformation here exhibiting E as the left can extension of D along F, okay? And B and Q small presheaves are connected by a partial evaluation. So this time, instead of diag, we do this with P, so an element of PPC such that connects those two. If and only if they are images of diagrams sitting in the can extension. Left can extension. Sorry, I was slightly imprecise. So in the A statement, F necessarily has to be a split of vibration. In the B statement, F is just any functor, okay? So, but the idea is that, so P, as we said before, P of C is like blueprints of colimits, and you can concentrate by taking somehow colimit of some of its parts, just like here you first sum 3 and 2 to get 5. If in a presheaf you somehow concentrate some of the parts by taking their colimits, you get a new presheaf. And that's the same thing, so to say, as taking the can extension of the diagram that has given you that presheaf. Okay? So a lot of people think of at least pointwise kind of extensions. So these are pointwise because C has to be co-complete and I and J are small. Pointwise kind of extensions as somehow colimits that are done piecewise, and this statement actually makes that intuition extremely precise. So that's like exactly what's going on if you use partial evaluation and instance them for the case of colimits. All right, so I think I would like to stop here. Let me just give some acknowledgements. So thanks to, I mean, well, of course, Walter Tolan, but he's not in the acknowledgement. He's actually also in the work. But so I want to thank in particular Bartosz Milewski and Fosco, because they explained coends to me.
Nah, stop
And
it.
also,
I did nothing.
Oh yes, you wrote an amazing book. And also David Myers for the weighted colimit part. So thanks to these people for, thanks to these people, because without you, I would not be able to figure out all these things. All right. And yes, I want to stop here. So
I
if you
guess
have
it's
any questions,
our turn to thank
please.
you, first of all, for your wonderful talk. That was very interesting. And of course, free questions. If you have, just chime in.
If you have any questions, please, or anything you want to see deeper or that you don't understand, please go ahead, feel free.
Yes. Paolo, may I ask a question?
Sure. Who is asking? I'm not seeing very well.
Paul André. So.
Oh yeah, hello. Yes, sure. Go ahead.
Probably. Yeah. So sorry, I would like to ask the question in Italian, but okay.
Oh, you can. I speak Italian.
Go ahead.
È difficile. So the question is this one. So you wrote this nice equivalence between having the same colimits and the zigzag property.
Yeah.
So if I understand properly, and I just want to check again. So the property has to do with size issues, because if you didn't care about size, yes, what you could do is just compute the factorization of D and
absolutely.
And then it would not be a zigzag. It would just be, I mean, it would be a zig followed by a zag. Yes. I mean.
Oh, you can. Yes.
You need a full zigzag, or you can do just.
You can do a zig followed by a zag, as you. That's a very good way to say that, actually. So the idea is that if you have I and J, it's true that you can take the growth and deconstruction of the image presheaf, which is the same for both functors because they both have the same image.
Yes.
Okay.
Exactly.
And the fact, so that would be D, that would be E, and there would be confinal functors this way.
Yeah.
Now, the problem is that this
is too big.
Is too big. However, you can take the joint full image of these two functors.
Okay. So that's the way you do. Okay.
That's going to be small.
Yeah.
And
this is confined.
And these are still confinal. Yeah. So yeah, that's how you get the zigzag. So it's again going to be a zig followed by a zag.
Yeah, but
why I put a zigzag in the theorem is that in practice, you will get zigzags so like sometimes one just has a zigzag and that's enough.
That was my question. I really enjoyed your talk, and I'm happy with the zigzag property, I think. But it's nice to know that you can do it in 2 steps.
Yeah. Yes, you can do it in 2 steps. But yeah, that was a good remark.
I have quite a naive question, if that's all right.
Sure. Who's asking?
Nathaniel Arkle.
Oh yeah, hello. Yeah.
So just related back to the original motivation as for Colimits as algebraic operations, I was wondering what the advantage to using this pseudomonad was over using the small presheaf pseudomonad directly and interpreting that as being an algebraic operation. Is there an intuition for?
Sorry, what's the question? I don't understand.
So if you want to view colimits as algebraic operations, you could instead
Mhm.
just start with the small pre-sheaf pseudomonad and interpret the multiplication as being the algebraic structure. So if you're
Yeah.
interested in colimits as algebraic structure, what advantage do you have in looking at this diagram pseudomonad instead of just looking at the small pre-sheaf pseudomonad?
Oh, I see. Well, I would say so one practical advantage, which is purely for practical reason, is that the monad of diagrams is a lot more nicely behaved than the monad of P. So in particular, so let me go maybe to a new page. So diag is, first of all, a strictive functor. And mu and eta are strictly natural. At least, I mean, of course, you could write but in the way I've written it, it's really easy to write this as a strictive functor. While P is, everything is done by universal properties, so it's actually only a pseudo functor. So in practice, it's a lot easier to work with diag because of this reason. But also because, so you've seen, if you look at the structure maps, so that takes a diagram and takes basically a choice of colimit of D. While here, if you have a presheaf, you start with a presheaf, small, and you get this complicated expression, which is basically okay, let's write it as a weighted colimit. The colimit of the identity weighted by P, which is a lot less, or I mean, okay, maybe let's also write it like, which is a lot less straightforward. So I would say it's true that somehow this is the real Frico completion monad, but in practice one does not. So in practice, let's say usually depending of course of what one does. Usually one takes colimits of diagrams, not really colimits of like weighted colimits over a whole category with weights given by presheaf. In the end, the result is the same, but I feel like this reflects. Oh, why do I? This reflects a bit more closely the standard mathematical practice of how one takes colimits. Plus, from so to say the universal algebraic perspective, so to say, we can think of like diag as some kind of a resolution of P or like a presentation of P. Presentation of P. So since especially since the comparison functor is essentially surjective, is something like diag quotiented by having the same image, image, which is like mutually confinal, is the same thing as P. So we can view diag as some kind of presentation of P, where the relations are given by this characterization of confinality. So again, of course, P is a lot more direct, but I feel like using diag kind of can give a little can give a better idea. At least to me, it gives a better idea of what's going on there. I don't know if this answers the question.
Yeah, that's very helpful. Thank you.
Oh, great. Thanks for the question, though. That's of course a good remark. Like I come from probability theory, where we have an analogous situation where P is like probability measures, like image probability measures of a random variable, and diag are more like the actual random variables. So the probability monad is really P, the one of probability measures, But in probability theory, it's sometimes more helpful to think in terms of random variables. And so yeah, it's a similar situation. Okay, are there any more questions?
I wanted to make a comment or just ask a question, which follows
Yes.
Paul André intuition, in my opinion. So
Okay.
is it, and maybe you can take it as a kind of deum, of course. Is it the case that this in factor that you have is a very strong notion of vibration, like a discrete of vibration or something like this? Because since in some sense you have an inverse, in some sense, of course, it might be the case that it is a strong notion of vibration, couldn't it?
So in some sense, it has it has almost a section. You mean, I suppose, right?
Yes.
I had a similar question, if I can jump in
Maybe yes. Let's answer
politely.
both if I can. Yeah.
What strikes me is that whereas we have shown like live that the diagram monad is not a Casey monad, the small presheaf one is a Casey monad.
Yes.
And
yes. It's like by
there is this result for one monad, but let's pretend everything works. There is this result that says that monads over a nice category can be turned into idempotent monads in a canonical way. This is a very old theorem by Fakir and rediscovered by other guys, I guess.
Yeah, you mean by taking this like free idempotent monad over a monad?
Yes. What if this map that you built is like a idempotentification of?
Oh, like a lax idempotentification.
Exactly, yes. Because it seems everything seems very canonical, and so at least you can conjecture that this works as a two-dimensional analog of the idempotentification of a monad.
This is not really true because the idempotent monad is, if you remember correctly, is a submonad of the initial one, and instead this one is a quotient of the initial one.
But probably when you laxify things, yes, probably. I mean, that's Fanta mathematics, but.
Yeah, so I don't know.
Would be nice to know. That's just.
Yeah.
and also, I mean, the confinality looks like, you are localizing the category. I mean,
yes,
it's another way to think of it.
Indeed, yes.
So,
yeah, so like in the sense of the quotient that I wrote here, right?
So yeah. So I mean, zigzag is fine, but you see.
Yes. Yeah, so it's a bit like when you have like a theory and you have some terms that may have some identities between them that you can kind of force to be equal. Here we are doing kind of that, except of course we force them to be isomorphic and there's some coherence to be taken into account, but that's kind of what's going on. So it's that seems to be what's happening.
I think the broad question is, how does the im functor that you define behaves? And that's interesting on its own right, I guess.
So what I know so far is that im is, well, essentially suggesting objects. It's a morphism of monads. And also that im from like for this is also essentially surjective object. Now that would have been obvious if this had been like so to say split surjective, like if you had a section, but it doesn't because of size issues. So you can't just map a diagram to its Grothendieck vibration factorial. But still, this is essentially surjective. I was wondering too if im was like an up vibration or a vibration. I don't know. It's a good question. But so that's what I've figured out so far.
But
I
I
guess.
think, you know, I mean, you mentioned at some point the action of two categories, yes, and the way diag should behave on two categories, and probably to bring some information. I mean,
I
but okay.
agree. So a full analysis here should involve also two cells, because naturally lives in two categories, because
Anyway, thank you very
of
much.
the multiplication.
Yeah. We have
So-
plenty of time to discuss this and other things in the free space. I guess
Mhm.
at some point, at this point, we can
Free space
thank
over
Paolo
what?
again. There is a slot of time for free discussion now.
Okay.
So I was just saying we have plenty of time there for expanding on this very interesting question.
Nice.
So
thanks.
let me thank you again. That was
Yeah, thanks.
an extremely interesting talk. So thanks, Paolo.
And thanks to the audience, actually, because you've answered some of the questions I had, in particular the KZAD question. Thanks a lot. I'm really happy.
Iteka
This is
saves
very
the
useful to
day.
me.
Okay, so thanks to you and to the audience and to the other organizers. And I guess I can stop recording now.